So for the first one, 5 gallons going into pints. Now we haven't seen this before where we don't have a direct relationship between the two, but we can go through a couple of steps if we want to. We got gallons on bottom. We don't have a direct relationship from gallons to pints, but we can go from gallons to quarts. 1 gallon is 4 quarts. Now the gallons have canceled out, but we are in quarts. We want to be in pints, so we got to get rid of our quarts. And we do have a relationship from quarts to pints. 1 quart is 2 pints. So we can keep going with this conversion factor. We can actually convert multiple steps to get from one to the other, canceling out the gallons first, ending up at quarts, canceling out the quarts then to end up at pints. And now we can multiply across the top. 5 times 4 is 20, times 2 pints is 40 pints. Across the bottom, 1 times 1 times 1 is just 1, so that is just 40 pints. Any questions on that one? Okay, for number 2 on the metric, going from liters to milliliters. We got liters, deciliters, centiliters, and milliliters. From liters to milliliters is 3 spots to the right. Decimal point goes 3 spots to the right, 730. Number 3, fluid ounces going into pints. Once again, we don't have a direct relationship from fluid ounces to pints. We can go to cups though. 1 cup is 8 fluid ounces. That would leave us in cups. We've got to get to pints now. So cups on bottom, pints on top. 1 pint is 2 cups. So on top, we've got the 80 times 1 pint. On bottom, we've got 1 times 8 times 2 is 16. 80 pints divided by 16 is 5 pints as our result. $490 milliliters to liters. Milliliters to liters is 3 spots to the left on the chart. My decimal point goes 3 spots to the left. That's 0.49. Two pints going to tablespoons. Well, we don't have a direct relationship to pints, from pints to tablespoons either. So we're going to go from pints to cups. Oops. Has to be pints on bottom so they cancel out. 1 pint is 2 cups. Get rid of the cups and go to, well, we can go to fluid ounces, and then, but we do know that there are 16 tablespoons in 1 cup. So we can go direct. If you didn't remember that one, you could go off of what we did yesterday. You could go from cups to fluid ounces, 8 fluid ounces in a cup, and then from fluid ounces to tablespoons, 2 tablespoons in 1 fluid ounce. Should end up with the same thing. So 2 times 2 is 4, times 16 tablespoons is 64 tablespoons. On bottom, it's just 1 times 1 times 1. So that is 64 tablespoons. Finally, number 6, 40 gallons going into bushels. Anybody remember the relationship between gallons and bushels? 1 bushel is 8 gallons. Good. So the gallons cancel out. 40 divided by 8 is 5 bushels. Any questions on any of those? Okay. So now, the other questions I like to pose look something like this. It's going to demonstrate the ease in the metric system versus the standard system. I'm going to have two similar problems. This first problem here, boy, those don't turn out to be anywhere near the same size. But the first problem here, we are going to have, let's see here. Let's say this is 4 meters by 3 meters by 2 meters. I want to find the volume and then the capacity in liters. Well, how would I find the volume of a box? Remember that from a few weeks ago? Length times width times height, which gives us 24 cubic meters. Now, if you recall from yesterday, we mentioned 1 milliliter is equal to 1 cubic centimeter. So if we can convert our 24 cubic meters into cubic centimeters, we can get to milliliters. 24 cubic meters is going to be how many cubic centimeters? Well, from meters to centimeters on the chart is 2 spots to the right. Since it's cubed, we have to move the decimal point. 3 for every one, right? So 2 spots become 6. So 1, 2, 3, adding those zeros. 4, 5, 6, adding more zeros. That is 24 million centimeters cubed. 24 million cubic centimeters is how many milliliters? 24 million. 1 cubic centimeter or one is 1 milliliter. They're the same thing. Then to go from milliliters to liters, well, to get from milliliters to liters is 3 spots to the left on our chart. So we move the decimal point 3 spots to the left. That's 24,000 liter tank. Not so bad. So the math is really simple. There's no major conversion. It's just a matter of moving the decimal points to get from cubic meters into liters. Over here, if I tell you that this is 15 feet by 10 feet by 6 feet, and I want to find its volume and its capacity in gallons, there's actually fewer steps. It's just more difficult. Notice over here, once I had this multiplied out, I did the rest of that without a calculator. There was no need to calculate anything. It's moving the decimal point. Over here, it's not going to be quite that simple. The volume will be length times width times height otherwise known as 900 cubic feet. To turn that from cubic feet into gallons, 900 cubic feet over 1. Who remembers our relationship between cubic feet and gallons? One cubic foot is 7.48 gallons. 6,732 gallons. So it's fewer steps, but you had to have the calculator to make this conversion. On the metric side, yeah, there's a couple of steps you have to go through, but each conversion is pretty simple, just moving a decimal point. Okay, so today we want to talk about, similar to yesterday, we made that distinction between volume and capacity. Today I need to make the distinction between mass and weight. Just like volume and capacity, we tend to use them interchangeably. However, in volume and capacity, they really are interchangeable because volume and capacity both, as we said, just measure how much can be contained within something. Mass and weight are actually very, very different things. Mass is the amount of matter in an object. The amount of material in that object, basically. Matter is just stuff, particles. Weight is a measurement of the force of gravity on an object. Are they related? Of course they are. The more mass an object has, the more gravity is going to pull on it. However, they are not the same. Mass is measured with a balance. A balance is basically a teeter-totter. Of course, a very precision teeter-totter, where we put the object we're trying to measure on one side, and on the other side, we put known masses. And whatever known mass balances our object, that is the mass of that object. Gravity is measured with a scale. Now, a scale really is a spring. A good spring stretches related to the force that's applied to it. If you double the force, it stretches twice as far, to within a limit, of course. So the way it's going to work is you take a good spring, and the word scale actually comes from the fact that there is a number scale on it. So the bottom of that spring is going to be your 0 point. That's where that number scale is going to start. It's going to number down through there. Now, when you place the object on it, you hang the object on it down here, that spring stretches. So this indicator that started here at 0 is going to slide. It might move down to there as the spring stretches. The amount that spring stretches is that measurement of the weight. We might be looking at that saying, well, that's not really different. Both of them involve gravity. Well, here's the big difference. Let's say we go to the moon, and on the moon, gravity is about 1/6 of what it is on Earth. It's going to change how much it pulls down on this object on the balance, but it's going to change how much it pulls down on the known mass as well. So the same known mass is still going to balance that object. However, on our scale, if there is less gravity, it's going to stretch less. So the weight has changed because gravity doesn't pull on it as much anymore. So mass is constant. Mass is a property of the object. Weight depends on gravity. If the force of gravity changes, the weight will change. We tend to flip-flop back and forth between weight and mass, almost considering them the same thing, because on Earth, gravity is relatively consistent. The acceleration of gravity is 9.8 meters per second on Earth. That varies slightly from the equator to the North Pole. At the North Pole, it is slightly higher. At the equator, it is slightly lower. Less than a 10% difference. Somebody who weighs 200 pounds on the North Pole would weigh in the mid 180s at the equator. So there's a little bit of difference, but not a lot, not a tremendous amount. When we look at standard measurement, we tend to focus on weight. So I'm going to talk about mass quick first. Just because most people don't even know that there is a unit of mass in the standard measuring system. In the standard measuring system, the unit of mass is a slug. You may have heard the expression, there's a whole slug of those. That's where that comes from. If you want to equate it to pounds, one slug is approximately 32 pounds on Earth. I had to put the Earth qualification in there because the pounds does depend on gravity. You'll probably never hear that term slug again used in measurement. May hear it used in expressions, but never in measurement. Because in the standard system, they tend to focus on weight. So let's start out with one of our larger units, the ton. How big is a ton? Typically, when we think ton, we think 2,000 pounds. That is what is called one net or short ton. It implies that there's something called a gross or a long ton. And there is. A gross ton is 2,240 pounds. 99.99% of the time, when you hear the word ton, they mean net ton. In this class, we will not use the gross ton at all. What's the difference? Where'd they come from? Well, the ton was originally used for buying and selling grain. If you try to put a ton of grain on a scale, you can't just stack it up and pile it up. It's going to fall off. So they needed a container. Well, if you think of your paycheck, if you work 40 hours a week at $10 an hour, you've earned $400. That's your gross pay. Do you actually get that much? No, they take out taxes and other stuff. You might get $300 out of that. Same thing here. Gross ton was the weight of the grain plus the container that held it. The net ton was the actual amount of grain you got. So the standard size container that was used to hold what they called a ton of grain weighed about 240 pounds. So obviously going smaller, the next unit's probably going to be the pound. Now it would make sense to abbreviate pounds PD. However, in the bookkeeping system for buying and selling grain at the time, PD was already used as the abbreviation for paid. So what they did was they used the Latin word for pound, which is libra, and they abbreviated pound LB. What's our next unit smaller than a pound? Ounces, right? How many ounces are in a pound? Careful. 16. If you're in the right country, 12 would be the right answer, but 16 in the United States. Now they chose to abbreviate ounces from the Latin word for ounce as well, which I can't remember at the moment, but it's not important. It's abbreviated OZ. Smaller than an ounce. This one sounds metric, but it isn't. A dram. There are 16 drams in an ounce. Smaller than a gram, there are units that we don't use anymore, like minims. One that we do use is a grain. For some reason, they don't do grains off of ounces, they do it off of pounds. 1 pound is 7,000 grains. Drams were the start of what we call apothecary units, but drams are actually a little large for medications. They might prescribe 1/8 of a dram of a medication for you, or 1/16 of a dram. So grains were really what was used for the more powerful medications. You might get 80 grains of the medication, or 20 grains even of the medication. Literally, it was grains of salt, counting them out with the tweezers. Not a job I really want. That's why pharmacists used to get paid big bucks, was they literally had to sit there and count out the medication. If you had 80 grains of medication, they had to count them out and put them in the capsules for you. Like I said, there's minims and stuff like that. There's 60 minims in an ounce and so forth that we're not going to get into. One thing I do want to mention, though, some weird units for you. You may have heard of a stone. 1 stone is approximately 14 pounds. Those of you in dairy, you're probably very familiar with the hundredweight. What's a hundredweight? 100 pounds. Technically, by the way, a hundredweight did not start out as 100 pounds. A hundredweight started out as 8 stones. 8 stones is technically like 98 pounds. The hundredweight started out as 100 pounds, was turned into 8 stones, but as they had to adjust the size of these to make them convertible, that got lost, so it doesn't really work anymore. Now, one thing you probably hear a lot about if you listen to the news, any financial reports at all, you may hear, the price of gold has hit $1,700 an ounce or whatever. We had mentioned that, King Edward had declared his thumb and his foot the official measurements of the land. Well, other rulers did the same thing at different times. So standard measurement was anything but standard as you went around the world. From one country to the next, or at the very least one region to the next, these measurements could mean different things. Well, the ounces and the pounds that are used for buying and selling gold are not the U.S. ounces and pounds. The center for buying and selling precious metals, starting back several centuries ago, was the island of Troy in the Mediterranean Sea. It was actually a center for trading a lot of things. It was an island right off the Greek coast, but it was nice because it wasn't part of the mainland, so there was no danger of invasion by letting ships come there. So they could come there and they could trade there, but it didn't endanger the mainland of Greece. So it became a very thriving trading post, basically. Well, in Troy measure, 1 Troy pound is equivalent to about 0.82 of our standard U.S. pounds. So a Troy pound is significantly smaller, about 18% smaller than a U.S. pound. One Troy pound, however, only contains 12 Troy ounces. So a Troy ounce is actually slightly larger than actually significantly larger. It's about 14-15% larger than our standard ounce. So when you hear that on the news about gold being $17 an ounce, it is not a standard regular ounce. It's a Troy ounce. It's a little bit bigger than what you would think of as an ounce. In the metric system, the metric system tends to focus on mass. So we're going to start talking about weight very briefly. The unit of weight in the metric system is a Newton. The Newton, by the way, is one of the few units in the metric system that does not fit in really well. 1 Newton is approximately 9.8 kilograms. Sorry, the other way around. 1 kilogram is approximately 9.8 newtons. Get that right. Now, again, you probably won't hear about newtons much. You might hear newtons more than you hear about slugs, but you still won't hear about newtons much. The unit of mass in the metric system is the gram. A gram is about the size of a paper clip. The technical definition of a gram, it's the mass of 1 milliliter of water. So remember, 1 milliliter is 1 cubic centimeter, 1 centimeter by 1 centimeter by 1 centimeter. You fill that up with water, that's about a gram. And then, of course, it's abbreviated with a G. We go smaller, we got decigrams, centigrams, milligrams. If you skip a couple, you have micrograms. Micrograms, again, is getting into your medications. Going larger, you got decagram, hectogram, and kilogram, which is the one we're probably most familiar with. Skipping up again, you've got a megagram, which is 1,000,000 grams. Now, the megagram became popular enough that we actually gave it a name. It is a metric ton. It is defined, rather than being defined as 1,000,000 grams, it's defined as 1,000 kilograms, which is the same thing. You have a kilogram's 1,000 grams, so 1,000 kilograms is 1,000 times 1,000, or 1,000,000 grams. 1 kilogram, by the way, and we'll talk about this more later when we do metric to standard conversions, is about 2.2 pounds. So a metric ton is about 2,200 pounds, a little bit bigger than our standard ton, but it's close enough that we can use that metric ton for trading with other countries, and it doesn't significantly change the way we do things. And of course, all of our conversions here are the same. But the biggest thing you can see here, if you link this back to what we've talked about before, is there is that link from one unit to another in the metric system. 1 gram is equal to, like we said, the mass of 1 milliliter of water. So 1 milliliter of a fluid is approximately 1 gram, as long as that fluid is close to the density of water. 1 milliliter is 1 cubic centimeter. So there's that tight link. Now that we have both capacity and mass defined, we can talk briefly about something called density. Remember, mass was the amount of matter, the amount of particles in an object. Density is how tightly packed those particles are. Density is defined as mass divided by volume. And it is volume, not capacity. It's cubic centimeters, cubic millimeters, not, liters or milliliters or anything like that. So if you have an object that has 280 grams of mass and fills 70 cubic centimeters, it'll have a density. The mass is the 280 grams. The volume is the 70 cubic centimeters. Its density is going to be 280 divided by 70, which is 4. The units then will be grams divided by cubic centimeters. So grams per cubic centimeter. So whenever you see this unit here, 4 grams per cubic centimeter, there's two things that you need to think of. One is, it is what's called a unit rate. It's really 4 grams per 1 cubic centimeter, 1 centimeter cubed. This is the form you'll need it in to calculate with it most of the time. The other one comes from kind of both of those, is what this is saying is for that object, for that material, 4 grams is equivalent to 1 cubic centimeter. The reason I bring that up is when we're doing calculations, if you don't remember this formula, you don't remember any of these formulas, in fact, we can use that same strategy we did with our unit conversions to do calculations. For example, if we have something that is, let's say we are told something has a volume of 25 cubic centimeters and a density of 6 grams per cubic centimeter. And we're asked to find the mass. When we look at a rate like this, 6 grams per cubic centimeter, if we think of it in this second form here, 6 grams per cubic centimeter means that 6 grams equals 1 cubic centimeter. We can use that to perform this calculation without really knowing anything about math. Just like in our conversions that we've done, the units will tell us exactly what to calculate. So we're starting out with 25 centimeters cubed, cubic centimeters. We're going to put that over 1. Then we are going to use this equivalency to do a conversion. We want to go to mass. What units is mass going to be in? Grams, right? So we want to go from the cubic centimeters into grams. Our relationship is 6 grams equals 1 cubic centimeter. So the cubic centimeters cancel out. We've got 25 times 6 grams is 150 grams. 1 times 1 is 1. So the mass of that is just 150 grams. If I wanted to go the other direction, let's say I have an object that has a mass of, let's see here, 154 grams and a density of 7 grams per cubic centimeter. Again, I'm going to look at that 7 grams per cubic centimeter and say that 7 grams equals 1 cubic centimeter. So if I'm asked to find the volume, I can again just use that unit conversion. Starting out with the 154 grams. Put it over 1. Now grams have to go on bottom, so I'll go to cubic centimeters on top. 7 grams is 1 cubic centimeter. This time the grams cancel out. That's 154 cubic centimeters over 7. So divide by 7, that's 21 cubic centimeters. So you can see this unit conversion method that we've talked about is called, the fancy name for it is called dimensional analysis. And it's really an extremely powerful tool because if you're trying to do calculations, if you look at the units on the numbers, many times you can use those units to tell you what you have to do in the calculation. You can, I'd say about 80 to 90% of all the calculations in science that deal with with these units. You can use the units to figure out what you have to do to calculate it, even if you can't remember what the formula is. Okay, time to let you guys get to work. In that packet still, on page 238, 51 through 56, deals with standard units of weight. Page 266, problems 49 through 54, deal with metric units of mass.